Hello everyone, my name is Rafael and I'm going to be presenting our work, Energy Constrained Drone Delivery Scheduling. Delivery drones are emerging as a new trend among the e-commerce companies. They are a promising alternative to inefficient and slow ground vehicles, but drones are limited by payload capacity and they can fly only for about a half of an hour in good weather conditions. Considering that 86% of all orders shipped by Amazon weigh less than 5 pounds and can potentially be delivered in small packages by drones, our paper presents a new scheduling mechanism that uses a multi-source A-star algorithm variant to compute safe distance and collision-free trajectories. The proposed mechanism is also constrained by the vehicle battery capacity and meets the on-demand requests deadline. For instance, we have the following setup in the Miami downtown area, and we need to schedule a large number of requests to deliver packages from the warehouses to the client delivery locations. So how do we do that? The drones use an aerial system that is represented by a directed graph where each edge represents an aerial lane. There are also charging stations along the path, and the drones can use them to recharge the battery and increase their flight range at most twice. In our problem, we consider that client requests can arrive at any time. The flight time is limited by the battery capacity. The objective of our work was to design an efficient and on-demand UAS delivery scheduling which accounts for the battery constraints and is collision-free. The routes we compute will depend on how we allocate drones to perform the deliveries and which paths are available during a specific point in time. During the initialization phase, we transform the graph into a unit graph, and we use a time-space graph to avoid collisions. We also divide each edge into segments of length d. We run the breadth first search algorithm over the unit graph, starting from each charging station, only for distances less than or equal to the flight range h. In the second phase, we run the BFS again for each client request, using now the client vertex as a source and limiting the search to radius of at the most 2 h edges. After that, each node in the graph within distance 2h will have the shortest path to the client vertex. Each warehouse that contains the product requested by the client and it is in range will be initialized as a root node of a new search tree. Our heuristic will select a best path among the feasible paths. If the path is found, we set the parameters, score, and we add the path to the priority queue. Our A-star variant will manage all new requests and assign the path to the drones, minimizing the chance of collisions and battery depletion, and also respecting the delivery deadline constraints.